At Astra is our mantra. At Astra to the stars. At Astra, it's who we are.
Welcome to Around Space. I'm Kent Miller. Today we're going to be talking about asteroid mining. I'm delighted to have with us Marshall Eubanks. In 1977, he got his bachelor's in physics from MIT. In 1980, he got his master's in physics, also from MIT. And then he started working for JPL, the Jet Propulsion Laboratory. In 1985, he became the visiting astronomer at Paris Observatory. And in 1988, he became an astronomer at the Naval Observatory here in Washington, D.C. In 2000, he became the Chief Technology Officer of Telesuite, and that's a company that invented telepresence equipment and technology. In 2002, he was the founder of America Free TV, and in 2012, he became the founder of Asteroid Initiatives, and their mission is to develop the economic potential of asteroids. Welcome back to this table.
It's a pleasure to be here again, it really is. So, I think people think of asteroid mining, which has a long history in science fiction. If you were a science fiction reader, you know, I was as a kid, you know, you were reading. It's funny how they tend to be like dirty coal miners or something, which of course is probably not a good analogy because it's a different technology in a different world, literally. And it's only really been fairly recently that it's possible to even consider asteroid mining. So there's multiple companies, there's Planetary Resources, there's the Deep Space Initiatives, both of which have had some, you know, discussed some plans, and there's my company, which is also trying to get something together in this area. I think, having researched this, done due diligence on this, I think this is going to be a long process. This is a long-term process. It will not be, oh, next year we're going to go mine asteroids. I think if we do this in a decade, we'll be doing fairly well, frankly. But I also think there's a huge potential out there. And the exact amount of the potential has to do with what we're going to be doing in space, of course, which I think is also developing in a fairly nice sense. I mean, things are, I don't know, if you were a space nut like I was, the 80s and the 90s seem sort of depressing periods because not a lot was happening.
That's right. Not a lot of forward motion there.
There wasn't a lot of forward motion. Yeah, the shuttle was flying and people were going up and you know, and in the beginning, even the space station, a lot of people thought, well, what really are they going to do with it? It's orbiting, but they're not going to be assembling spacecraft or anything. And I mean, actually now the space station has developed into a really nice research tool, and so research, you know, laboratory, and you know, it's developing its potential, but we got to get off the planet, and we got to get people off the planet. Now we're thinking of asteroid mining with you know, probably with robotic spacecraft, but I think first we're going to be doing prospecting more than mining, and so it's not just mining, it's also planetary defense, because an asteroid, there's the Earth behind us, an asteroid could come in and hit the Earth and, you know, kill the dinosaurs.
So some of them are in orbits that are near, or at least pass near the Earth.
Yes, and in space, distance is really, as you probably know, distance is not really the important thing. You know, you think, oh, the distances are huge. Well, yes, the distances are huge, but what's really important is the velocity you have to get, the so-called delta V, or change in velocity. And that directly drives your cost. So, you know, you can go faster or slower or whatever, but there's always a minimum delta V it takes to get from here, Earth, to some other orbit. And the higher that is, like if you go out to Jupiter, that's a high delta V, it takes more energy. Yes, it takes longer, but that's not the real problem there. It just takes more energy to get there, and you can't get around that.
So it's more costly.
So it's more costly. And so that means that for the foreseeable future, we're not going to be sending huge vessels out to the asteroid belt, because that takes a lot of energy. It takes more energy to go to Ceres than it does to go to Mars, and we know Mars is a fair amount of energy. what we're going to be doing is we're going to be going to asteroids that have orbits close to the Earth's orbit.
I see.
Because those are the ones that have low, as they, in the jargon, low delta V. The energy to get to them is low. And those are also the ones that are potentially of danger to the Earth, precisely because their orbits are. So those two things dovetail very nicely. The study of, and of course there's a scientific interest.
There's a linkage.
There's a linkage.
Planetary defense and the prospecting of
Yes.
these. Yeah.
And so in fact, we have been involved in a mission, a potential mission. It hasn't really been officially selected yet, and our role hasn't been officially selected either. It may not be, for all I know. But I think it's really fascinating. A mission to an asteroid called Didymos, which is a binary.
Okay.
So it's like the Earth and the Moon
Co-rotating or
co-orbiting.
co-orbiting. Yep.
You have a big thing that's about a kilometer across, not quite half a mile, say, a little less than a kilometer, and then a cigar-shaped thing that's about the size of a football stadium circling around it.
Okay.
And the idea is that you have a European spacecraft goes, deploys instruments, backs off, and a American spacecraft, this is a joint European-American mission, will, at the time of closest approach, so astronomers on the Earth can get a good look at it, and you can use radar and optical and so on, a spacecraft called DART comes in and hits the secondary at about 6 kilometers a second, which is enough momentum, it's about 300 kilograms rather, enough momentum to change the velocity of the secondary by about 1/3 of a millimeter per second.
If the secondary holds together.
If the secondary holds together. Well, that's part of the point, right?
Okay.
Suppose instead of a secondary, this was something that was going to hit the Earth.
Sure.
So, well, one thing you might say is, well, we'll hit it with a so-called kinetic impactor. We'll throw no pun intended, a dart at it.
Right.
Well, will that cause it to break up into pieces? Which could be worse than having it together, you know?
Yes.
Instead of hitting one city, it might hit 10 cities, you know, or something,
Right.
depending on how many
Get
pieces.
a big debris cloud that hits everything.
Will it, I mean, if you hit it, ejector's going to come off. What is that going to do to the momentum change? You don't really, you know, 1/3 of a millimeter per second assumes, well, you have to know the mass, but assumes basically all the momentum goes into moving it. Well, maybe all the momentum won't go into moving it. Maybe the ejector will increase that or decrease. It could go either way.
Right. And the ejector usually comes out as a cone in the backward direction. So actually the momentum transfer could be greater.
Yes, the momentum transfer is expected to be greater.
I see.
But it's, you know, you don't really know until you do it.
Yeah.
And you certainly don't know by how much greater until you do it.
Yeah.
And so, and that's part of the goals of the mission. And so but that's very close to asteroid prospecting
Do
too.
we actually know if this smaller asteroid is a single monolithic rock?
do not.
Or is it just a rubble heap?
The conventional wisdom, the theory is, the primary actually rotates quite fast. The primary actually rotates about as fast as you would expect an asteroid to rotate, and
So it might be a
maintain
single
its
rock.
cohesion. No, it probably isn't either.
Okay.
The primary, we know, because of radar, has an equatorial ridge going all the way around it. And why would you have that? Well, there's something called, in the asteroid world, called YORP, Y-O-R-P, which is an acronym. But YORP is when solar radiation hits an asteroid, it heats it up. And both the reflected radiation and, more importantly, the heat, the infrared from the heated parts, act as little rockets that both perturb the orbit of the asteroid and its rotation. They can spin it up or spin it down. And YORP frequently spins up asteroids until they spin as fast as they can until they start falling apart. Well, they don't just fall apart in like all at once.
The loosest material goes first.
The loose material on the equator goes first.
Yeah.
And so, and material that's loose, like at the poles, will tend to flow down to the equator. So that's why we think, we don't know, but we think there's a ridge from that process, the material flowing down to the equator, and then material flowing off the ridge into orbit around the body would coalesce to form the secondary. So we think, again, we don't know, but we think that the secondary is just a bunch of rubble, literally, that's fallen off the primary. And in fact, so there's fundamental science here, right? None of this, this has all been tested or thought of remotely, but there's no proof of any of this.
We don't know until
we don't
go
know.
there.
Well, we will, if all of this works, we will know.
Yeah.
And so that's kind of cool right there.
Yes, indeed.
So yeah, it's a rubble pile. And in fact, another interesting thing about these small objects, and I'm going to show a couple of figures here. So the first figure is a picture of an asteroid called Ida, which was passed by the Galileo probe a couple of decades ago. Ida is a big 60-kilometer asteroid. It was one of the first to actually have a good picture taken of it.
Yeah.
And at the time, it seemed like just natural. If you'll look at this picture, it's covered with craters. It looks like the surface of the moon, the surface of Mercury. Most of the objects in the solar system that are old, that don't have stuff going on,
Mars. Yeah.
look like, well, parts of Mars. Parts of Mars are
right.
resurfaced, but parts of Mars are full of craters too.
Yeah.
So Ida looks like, really, I mean,
It's what we
just
would
from-
expect. Yeah.
Exactly. When I saw it, it's like, okay, it's another one of these things that's full of craters, nothing to see here, move on, kind of. But the next picture is a picture of this asteroid that's only 500 meters, a little less than half a mile long, that's called Itokawa, that a Japanese spacecraft called Hayabusa went to. And you will see it has no craters.
Yeah,
And
that's suspicious.
that's odd. And the oddness, sort of, now that we have radar on Earth can look at asteroids that come close to the Earth, can look at even small ones. None of the small guys seem to have craters. And so why?
That would suggest, are they young?
Well, they shouldn't be young. Yes, I mean, people thought, well, maybe Itokawa was like spalled off some bigger asteroid. It's just some piece that was flown off by a meteorite impact or something. But having not, sort of one is an accident and two is a coincidence, but three or more means something deeper.
Something fundamental is happening here.
Yeah, something fundamental. And we think, we don't know, but we think what happens when a big meteorite hits such a body, the whole thing shakes and any craters or whatever disappear. Well, again, we don't know that. So we're going to find that out with DART, hopefully. And what we
So
propose...
it's like if I had a box of sand
It shook it, yes.
and I shook it, then any features would settle out. Yeah. Okay.
And,
Smooth out.
And there's, in my opinion at least, a lot of the details and the physics of this are very poorly understood. Why does the asteroid not just fall apart? You hit it, why doesn't all the pieces just go every which way and there you go and you don't have an asteroid anymore?
These smaller asteroids are so small and the gravity is so weak.
Yes.
One would expect that any impact would just scatter it.
Yes. I mean, the two forces that we know work on an asteroid, one is gravity.
Sure.
And the gravity is a millionth the gravity on the surface of the Earth.
Yeah, you couldn't even walk on it.
Yes. I mean, if you dropped something, it would just hang there for your as far as you were concerned, it would just hang there.
Yeah.
You couldn't possibly walk on it.
Right.
In fact, if you tried, you would probably send yourself to escape velocity. I mean, escape velocity is only about a meter per second.
Right.
So you could literally
take one step and you're gone.
Yeah, take one step and you're gone. It would be hard not to. And the other is a so-called van der Waals force, which is a contact force when atoms are put together. And the trouble with that is, well, as soon as you get them even like a tiny amount, a fraction of a millimeter apart, there's no more contact force.
Right.
And so they will fly apart. So it's a stickiness. You can think these asteroids are sticky, the rocks or whatever, they're sticky.
So we'd expect a shock from an impact would break those bonds.
And then they're gone. Everything just and
gravel and sand flying in all directions.
Yeah, and that's either that doesn't happen, or it happens gently enough that gravity brings them back eventually together. We don't really know.
Okay.
And and
So
one of
plan
the
is to go hit one and see.
we're going to go hit one and see. And our proposal is to take little things like this that is printed circuit. This is not a printed circuit. This is a credit card, but take something like this. It's a printed circuit with measurement tools on it, like say an accelerometer.
Okay, which can be miniaturized.
Which can be miniaturized. And this is actually the size. I mean, this is literally, it might be square instead of rectangular, but this is literally the size we're talking about. Have solar cells on both sides, have maybe a little probe or something so it sticks into the surface maybe. Okay. Have a radio, of course, so you can get information back, and just put them on the surface. You could even have a little tiny camera. So you can take one picture. What does it look like,
Yep.
And put these all over the surface. And so a 1 kilogram payload could potentially be dozens of these spacecraft.
Right.
Maybe even more. And so instead of one spacecraft, you have dozens. And so now you can risk them. The fact that half of them might be destroyed by the DART impact is not that big a deal because you've got more. And so then we could see, how does the thing actually vibrate? How does, what's actually happened? Do pieces go flying off? if a piece goes flying off, well, maybe one of these will go flying off. You
Right.
know?
If the sensor flew off, you'd be tracking it.
You'd be tracking it for at least a little while, and if it's really escape velocity, it won't come back. But
But you will have had the accelerometer data.
you'll have the accelerometer data. You'll know what's going on, and so I'm pretty excited about this. I hope we get selected for a further. It's a multi-stage process. You know, the first stage is probably pretty easy to get into, but then it gets tougher until you actually get to flight hardware.
Yeah.
But
So you're looking at phase A
yes,
contract.
phase A. But if you think about sending a small spacecraft, say with a solar sail, past a bunch of asteroids, which is clearly the next step. Instead of going to 1, you go to 10, let's say.
So you do a tour.
Where you're going to do a tour where you're not going to be able to stay very long at each one.
Right.
And one of the things about solar sails that people don't appreciate, the sail is always wrinkled. Solar sails are powered by sunlight. Sunlight hits the sun, the sail, and gets reflected. So it's very much like Yorp, that it's a radiation pressure. The actual photons, there's a photon rocket, you could say, is driving this thing. The thrust is very low, but it's always on.
Right.
So it just builds up over time. Now, when you're saying, I want to go to this asteroid and I have a change in velocity, a delta V of a mile per second or something, which is like faster than any rifle bullet, you want it to be always on. It adds up over time. But when you get there, the always on part is annoying. If it was a big body, if it was a moon, like something the size of our moon, well, you would go into orbit and you could just orbit it. But these tiny bodies, the gravity is so weak, you'll just keep going on by.
Yeah, that's right.
And so, and the sail is too fragile to possibly say we're going to land. And of course, you can't really land anyway because the gravity is so weak.
Right.
Well, you take your little tiny guys, shoot them at the surface, and measure like chemical composition or whatever as you're going by. And you're not going by that fast until you have a week maybe when you're within range. And you do your experiment, then you move on to the next asteroid. I honestly think that if these are accepted, as this is developed, this will be done with every minor planet, minor body mission. That it'll just be part of the toolkit people use. NASA is actually interested in doing a very, very similar thing with little guys like this to the moon Europa of Jupiter. But that's much tougher.
It's a bigger job.
It's a much bigger job. The landing would be at several,
Well, the radiation environment on Europa is
very tough.
Oh dear.
Very tough. But our landing velocities will be about 50 centimeters a second.
Okay.
So that's equivalent to doing that.
Yeah.
So that it should survive. On Jupiter, it's about 2 kilometers a second, which is like being shot out of a cannon at a wall and surviving that. Oh, it's not impossible, but it's much tougher.
Yeah. Yeah.
And in fact, my understanding is they're thinking maybe taking 1,000 and hoping, a handful survive. Just,
Oh dear.
brute forcing it, you might say.
Oh dear.
So that's a mission that's coming up. It would be launching in 2020. It would be arriving there at 2022. I think you'll hear a lot more about it in the future. It's not been officially selected, but I think it's likely to happen. We hope Asteroid Initiatives is part of that, so that's another hurdle. But even if it's not, I think your audience will be interested in it.
Indeed.
And so you want to talk a little bit about the economics of this, which is a rather different matter?
Well, once you've done prospecting and you've selected some asteroids that may have economic potential, the next step is mining.
Make money from it somehow.
Right.
And that is an interesting question. I don't want to
Well, let's start with what minerals you would think would be economical.
Well, when Planetary Resources launched, they talked a lot about so-called platinum group minerals, which is heavy elements like platinum and the like that tend to occur together in the solar system.
Well, we have in our catalytic converters of our automobiles, we have palladium, is that right?
Yes.
Yeah.
And platinum is, of course, a huge
it's a catalyst.
Catalyst that's used in all kinds of stuff. And palladium is a catalyst too, right?
Yeah,
It's used in all kinds of stuff, but not a lot of it in a...
No, you need just a very tiny film, really.
Yes.
You need a lot of surface area. That's
You need
what
surface area, but...
so the substrate has tremendous surface area, and then you evaporate a thin layer.
And I actually was sort of like a little taken aback when I first heard the press reports, because I actually done some numbers on that and tried to figure out what would it cost if you could just get the stuff without any mining, without any digging it up or any machinery. You just go and grab it and bring it back. And I don't see how you could
Bring back the whole asteroid.
No, bring back platinum. Like there's platinum on the surface, like nuggets or something. You just go and grab them and bring them back, and not have to mine ore or refine it or any of that
So
good
assuming
stuff.
that there's bullion just stacked there,
Yeah, assuming there's
can you bring it back economically?
Yeah, aliens mined it for you. And
Okay.
they left the bullion when they left, It's just there to pick up.
Would the business close?
I don't think it would, frankly. I
Yeah.
think now Elon Musk says he's going to lower the price of launches considerably. If obviously if you keep lowering the prices of launches, maybe it would.
But I'm thinking he's talking about a factor of 2. I'm not sure.
He says a factor of 10.
Oh, really?
I've actually talked to him about it, but
Okay.
I think a factor of 2 is probably more realistic in the near term. Let's put it that way.
Yeah.
I can see a factor of 2. I mean, clearly,
Right.
I can see doing a factor of 2. A factor of 10 to me seems like ambitious. I mean, it's great to be ambitious. I'm not, more power to him. If he can do it, that's great. But I think you need at least a factor of 10 to begin to have this sort of, because remember, in my sort of toy model here, we're not spending any money to refine anything, It clearly, I mean,
Well, this is
you
then
will.
the problem, is you have a fundamental choice. Either you bring back the ore, or you refine the ore and its location, and then just bring back the concentrate.
yes.
Now, that's not so easy. Both are
Neither
problematic.
of those is easy, yes. I mean, if you bring back to where? If you start really talking about bringing back many tons of stuff,
Right.
you're not likely to bring it back to the Earth. You're likely to bring it back to, say, lunar orbit, because lunar orbit, you can find lunar orbits around the moon that are stable. And one of the things people worry about is you start bringing back many tons of stuff. Well, what if you get it wrong?
Right.
And instead of landing in the outback of Australia, it hits New York City, say, Manhattan, Central Park.
Unlikely, but disastrous.
Yes, but can you guarantee you won't, sort of?
Yeah.
And so if you put an orbit around the moon, you can find orbits where you can pretty safely say, no, this is not going to hit,
Right.
Even if, say we had a bad disaster and our spacecraft blew up and we couldn't fly another spacecraft, because that's one of the things people worry about is you have all this stuff going on, then you have a major disaster and you find, oh my God, our rockets are our design is bad.
Well, let's talk about the alternative. Now, I have a little bit of geology background. I used to work for an oil company, for example. If you're going to actually dig up an ore and refine it, you're going to need a lot of energy, you're going to need water, in some cases you're going to need detergents, other chemicals that you're going to need to get the uneconomical materials out and leave a concentrate.
Yes.
All right. Now the question is, do we have this technology to take to an asteroid a refining system?
No, certainly not. And we would have to develop that. Somebody would have to develop that. And that would be billions of dollars.
Yeah.
Now, if you had a good business case, in the oil business, for example, they're used to spending, look at those huge deep water rigs that,
Yeah.
those are not cheap. They're used to spending those kind of money if there's a payout. But I think it's the chicken and egg problem. Who is going to do the first thing like this to make money? Once you have a system going where you're going out there and coming back and so on, then adding a new thing is much more doable than starting the first one. In other words,
Right.
if you said, oh, well, we're mining platinum, but we could also mine gold, we just have to carry up this other chemical or something and use our same, robots to do it or whatever, well, then okay, you could probably make that work. But starting from scratch is a tough one. I personally think that the way that mining is going to develop is to supply stuff to uses in space. And that's likely to be fuel and consumables for biological creatures like us. And so fuel is going places,
Right.
and consumables is Mars for right now, because that's the place we're
So
planning
we're
on
looking at
sending people.
oxygen, we're looking at water.
Oxygen, water. I mean, one of the interesting things, Mars has 2 moons, as you know.
Yeah.
And the closer moon, Phobos, is likely to be the first human target for exploration. There's a mission called the Asteroid Retrieval Mission, or ARM, which has been fairly controversial. It got a lot of flack in Congress last week.
Well, it's going to have a prospecting element to it.
It definitely has a prospecting element.
All right.
But one of the aspects of Phobos that's interesting is we think it's a carbonaceous chondrite of a sort that would basically make it a fairly good petroleum resource.
Interesting.
It's like a big tar sand. It's like a big ball of tar
Okay.
sand or something. So would a Mars colony be able to use oil? Because if so, we know where to get the oil from. I mean, the idea behind ARM is it has two components. It has a manned component or a crewed component, and it has a robotic component. The robotic component goes to an asteroid, finds a boulder on the asteroid, grabs the boulder and puts it in its arms, kind of,
Right.
and then brings it to a high lunar orbit.
Okay.
The humans fly up to the high lunar orbit and inspect the boulder, which typical would be 10 tons, maybe, 10 metric tons. 5 to 10 tons, something like that is what the capacity
And decide
is.
what to do with it.
And then decide which pieces to bring back to Earth and which pieces to leave up there in this stable orbit. Now, if you think about it, that could be a boulder full of ore, right? Potentially.
Yep.
So, I mean, the technology is being developed that you could then say, okay, we can bring ore to this high lunar orbit and then do something with it. Now, that's not a complete business case because you have to bring a processing lab or whatever up to the high lunar orbit and, turn the ore into something useful. But, but you got that part down. But one of the things, the arm that's being developed at NASA, which I know something about because I've been involved with some of the people in discussions and stuff, it hasn't really been presented very well. The robotic spacecraft could be refueled by humans. The fuel is xenon, so it's an inert, benign fuel. Could be refueled by humans and has the delta V, the velocity change, to go to Phobos. Phobos is very easy to reach.
Right.
And grab a boulder from Phobos on the next round and bring it to the high lunar orbit. And then the astronauts could go to Phobos on the next round of that. And so it's actually a path to get to Phobos.
Alrighty. Well, thank you.
And then they will need resources, and we hope we could, at that point, provide them with some resources from asteroids.
All right. Well, thank you very much.
Thank you, sir.
All right. And that was Marshall Eubanks, is the founder of Asteroid Initiatives. Thank you for joining us, and see you next time.
Thank you.